Okay, thank you for the introduction. So hello everyone, I'm Ariel, and this is a joint work with Yehuda Lindel. So in this work, we consider the setting where we have n parties who wish to compute jointly some functionality, and the functionality is represented by an arithmetic circuit over some field. The computation is carried out in the presence of a malicious adversary who control up to half of the parties, which means that an honest majority is assumed to exist. So if we have 5 parties, then exactly 2 parties may be corrupted. And our security definition is security with a vote. Although in the honest majority setting, fairness, for example, can be achieved, in this work, since we want to achieve the highest efficiency possible, we consider only security with a vote, which means that the adversary may cause an abort, but if an honest party received its output, then this is the correct output, except for negligible probability. So our main result is 2 compilers from semi-honest to malicious security. Both compilers work with protocols that are based on secret sharing, and both are information theoretic. Our first compiler, it works for any number of parties, but it is designed and optimized for small number of parties. Our 2 best instantiations using this compiler are a protocol that for a multi-party computation with that uses the Shamir secret sharing scheme and requires each party to send 4 times n-1 filled elements per multiplication gate, and a protocol for the 3-party case that is based on replicated secret sharings and requires each party to send exactly 4 filled elements per multiplication gate. Our second compiler also works for any number of parties, but is optimized for large number of parties, and the best instantiation using this compiler is a protocol that is based on the Shamir secret sharing scheme and requires each party to send exactly 42 filled elements per multiplication gate. So the overall communication complexity per multiplication gate is linear and grows linearly with the number of parties. Okay, so before proceeding, a few words about honest majority MPC. What do we know about honest majority MPC? So we know that it is much, much faster than this honest majority MPC. It's not even comparable. We know that if we restrict the number of corrupted parties to less than third, then it is an easier case, and that already 10 years ago it was shown that full security with perfect security and linear communication complexity can be achieved. And also there was concrete efficiency implementation, the VIF implementation, which even today, at least for a small number of parties, should perform very well. In our case, when the adversary can control more than a third of the parties but less than half, then to achieve full security with linear communication complexity is much harder. But it was shown that it can be achieved in the computational model. But to achieve that, for example, the work of Hirt and Nielsen, they used expensive public key cryptography tools. They used polyerror encryption, so it is far from being concrete efficiently. In the information theoretic model, the best known result, to our knowledge, is the result of Ben-Sasson et al. With n log n communication complexity. If we look only on security with a vote, as in our case, so we are not the first one to achieve linear communication complexity. It was achieved in 2 previous work, but our constants are better, and also we provide a concrete efficiency, full implementation for any number of parties, which was not done before. Okay, so let's start with a high overview of our compiler. So as in any protocol that is based on secret sharing, our protocol or our compiler starts with the parties sharing their inputs to the other parties. Then we compute the circuit using some semi-honest protocol. And then, because the adversary is malicious and might cheat, we run a verification step where we verify the correctness of all multiplication gates. Why only multiplication? Because in other gates, the there is no interaction between the parties, so the adversary cannot cheat. Only in multiplication gates it can cheat. And if this verification step have ended successfully, then we go on and reveal the output and give the parties their output. So from a first look on this process, it is easy to see that our semi-honest protocol must also be private in the presence of malicious adversary. Now this is easily achieved. All the protocols that are based on secret sharing that I know have this property. They are private also in the presence of malicious adversaries. And therefore, the only thing that we need to take care of is the correctness of the computation. This is what we do in the verification step. Our verification step follow the well-known Beaver method, where we generate Beaver triples in some preprocessing step and use them to verify the correctness of all multiplications. But in many MPC protocols, the requirement is that the Beaver triples will be correct. In this work, we do not require the Beaver triples to be correct, because we insert some randomness, we will see it soon, we insert some randomness into the verification that allows us to detect cheating even if the Beaver triples are not correct. And therefore, we can generate the Beaver triples in a very efficient way. And therefore, the most expensive part of our compiler is the verification step, which will be the focus of this talk from now on. Okay, so of course, for our compiler to work, the secret sharing scheme that is being used must have some operations and procedures. So it must have, obviously, some sharing procedure, some reconstruct procedure to reveal a secret to a single party, and an open procedure to reveal some value to all the parties. It also must have, of course, some private semi-honest multiplication protocol, and some protocol that we call F1 to generate random sharings. Now, with these building blocks, let's move to our verification method. So, a quick reminder about Beaver triples. So, a Beaver triple is a triple of sharings. A, B, and C are shared among the parties, such that A and B are random, and C equals A times B. And now, if we have some triple, X, Y, Z, that we want to verify that it is a correct multiplication triple, then we can use a Beaver triple to verify it in the following way. So we compute, using this formula, we compute a new sharing V. We open it, and if it equals 0, then we accept, and we say that this is indeed a multiplication triple. Otherwise, we reject and abort. Now, let's look closer on this process. So this is the well-known Beaver trick. So the first thing we ask is, what happens if the Beaver triple is not correct? So as I said before, by inserting randomness into this process, we can avoid the requirement of the Beaver triples being correct triples. So how does it work? We generate some random public value, alpha. We plug it into two places in the formula, as you can see here. And then it works. And then we have the property that if X, Y, and Z is not a correct triple, then the honest parties output accept with small probability, with probability 1 over the size of the field. And this is correct regardless of whether the Beaver triple that we use is correct or not. Okay, so this is the cheating probability of the adversary, 1 over the size of the field, and it is and this is the cheating probability regardless of whether the Beaver triple is correct, and therefore we can generate the Beaver triples in a very efficient way. Okay, so now let's look on this formula on step 2, the formula to compute this new sharing V. So as you can see, most of the operations in this formula are local operations. The parties can add shares locally, they can subtract shares locally, they can multiply share with a constant, with alpha locally, but there are two places in this formula, here and here, that requires the party to multiply shared values. Okay, this is something that cannot be done locally. So the parties must interact somehow. So how do we overcome this? So the standard way of overcoming this is by open values to the parties. If we open two values, if we open the value of alpha x plus a and y plus b, then first it's okay to open them because A and B are random, and therefore nothing is actually revealed. I mean, nothing is revealed about the private inputs. And now, if we plug this value, rho and sigma, into our formula to compute V, we have only local operations. Okay, so if we look at this verification protocol, which is our first verification method that is based on opening, we see here 3 opening operations, right? 2 in step 2 and 1 in step 4 where we open V. Now, as we show in the paper, we can batch the last opening, the opening of V, over many verifications. And therefore, the actual cost of this protocol is exactly 2 openings per verified multiplication triple. Okay, the 2 openings that we have in step 2. Okay, so this is the standard way of verifying using Beaver triples. Now, towards our second verification method, let's look on a simple observation. So our observation is that opening is an expensive operation because each party needs to send its share to all the other parties. Now, this is reasonable for small number of parties, but for large number of parties, at least in the honest majority setting, private semi-honest multiplication is in many times cheaper than opening. We have protocols for private multiplication that have constant overhead per party. And this is cheaper than opening, at least for large number of parties. So now let's go back to this process, to the verification process. And now, instead of opening, let's do here in these 2 places where we have multiplication of shared values, let's do private multiplication instead of opening. Okay? But this sounds a little bit weird at the beginning, right? Because the whole purpose of this process is to verify the correctness of a triple that was computed using private multiplication. So it looks weird because how can we verify the correctness of private multiplication execution by executing yet another time the same protocol, private multiplication, right? Not even once, twice we execute it here, right? So how can it work? Or in other words, how can we detect cheating in the computation of the protocol when what we do is actually give our evil adversary more opportunities to cheat? And indeed, if we use private multiplication, indeed this complicates things a lot. But as we will see in the next slide, we can do some changes in the verification protocol that would allow us to achieve still a secure verification protocol. So the first thing that we do is instead of generate a random public value alpha, let's replace it by generating a random sharing alpha. Okay, now this makes sense because before in the verification based on opening, the adversary actually could not cheat. In the opening, it can cause an abort, but it cannot cheat. Now that it cannot cheat, even in the middle of the verification verification process, then we must keep the randomness that we use as a secret. So this makes sense. But look what happens now. Now we have 4 places in this formula that where we have private multiplication, where we need private multiplication because we have multiplication of shared values, right? Because now alpha is a random sharing. So in the 2 places where we use it, we have again multiplication of shared values. But this is not a problem because if we use private multiplication with constant overhead, so executing it 4 times still brings us to constant overhead per party. Okay, so still for a large number of parties, this will be better than using 2 openings. So this is not a problem. A second issue well, it's not a change in the protocol, but a second requirement that we have here is that for this protocol to be secure, we need our private multiplication to have another property that we call secure up to additive attack, which means that whatever the adversary does, it can be reduced to an attack where a value is added to the output. Okay, a value that in the proof can be extracted by the simulator and so on. So this looks like a strong requirement, but fortunately, and we rely here on previous works by Genki, Nishai, et al. It was shown that many secret sharing-based protocols have this property. Okay, they are actually secure up to additive attack, so still, this is not a problem. We can still use a semi-honest multiplication protocol to perform all these multiplication between shared values. There are two additional changes in this protocol that we need to do in order for this verification protocol to be secure. The first is, we called it randomizing V before opening it, even if we, as I said before, batch the opening over many verifications. And the second is a change that we need to do in the verified triple, a change that, of course, will not affect the correctness of the protocol. I will not go into the details of these two changes. I will send you to see it in the paper, but I will say two things. One, that although these two changes are of high importance, they do not almost affect the cost of the protocol. And the second thing is that if you want to see the exact details, please look in the full version of the paper on ePrint, and not in the version that is in the proceedings, because in the proceeding, unfortunately, we have a small error there. Okay, so we apologize for that, but so please look in the full version of the paper. Okay, so if we add all these changes and requirements, then we can prove that this verification method that is based on multiplication works, which means that the cheating probability of the adversary is still 1 over the size of the field, okay, as the verification based on opening, and this whole protocol is still private, which means that nothing is revealed to the adversary. Okay, so let's sum up what we've seen until now. We've seen two verification methods. One, the standard way of verification based on opening, which requires 2 openings per each verified multiplication. And a second way, a second verification that is based on private or secure up to additive attack multiplication, need to require for each verified multiplication 4 multiplications and one random sharing generation. And of course, the actual cost depends on the way we implement fmult and frand. And this is exactly the time to see some instantiations. So we have 2 instantiations in our paper. The first one is for multi-party computation using the Shamir secret sharing scheme. We have 2 protocols to generate random sharings. The first is the PRSS protocol, which is non-interactive, but the computational work grows exponentially in a very fast rate. The second is what we call the Van der Monde protocol, because it uses the Van der Monde matrix, which is hyper-invertible, to batch the random sharing generation over many sharings. And the amortized cost per party is 2 elements that need to be sent per random sharing that we generate. Okay, for the multiplication, for private or secure up to additive attack multiplication, we also have 2 protocols, the GRR protocol, which requires each party to send n-1 elements, and the second, the DN protocol, Damgaard and Nielsen, which requires each party to send, on average, 6 elements per multiplication gate. Our second instantiation is for the specific case of 3-party computation. And here we use the replicated secret sharing scheme. And here we have a protocol to generate random sharings, which is non-interactive. And for the multiplication, we present a protocol that requires each party to send exactly 1 field element. So all this protocol, together with our 2 verification methods, we can have many, okay, so with all these protocols and the 2 verification methods, we can have many combinations here, right? And each combination, with each combination, we have a different protocol. For example, if we take, let's say, the PRSS protocol to generate random sharings, the GRR for multiplication, and the verification based on opening, we have the best instantiation for small number of parties. In contrast, if we take the Van der Monde protocol to generate random sharings, the DN for multiplication, and the verification based on multiplication, then we have a protocol that has constant overhead per party for each multiplication gate. And this is the protocol that requires, that I mentioned at the beginning, that requires each party to send exactly 42 elements per gate. Okay, and of course we have also for the second instantiation, we can have two protocols depending on the verification method. Now, we didn't implement all the possible combinations. We only implemented those who make sense. You can see the technical details here. We computed a very large arithmetic circuit of 1 million multiplication gates and depth 20. And we used two fields, 61-bit Mersenne prime and 31-bit Mersenne prime. But for the 31-bit Mersenne, we repeated the verification twice. Why? Because remember that the cheating probability is 1 over the size of the field. So if we want to have in these two fields the same level of security, then we can repeat the verification twice with different randomness, and then we can reduce the cheating probability in the second case and have almost the same security level in both for both fields. So, okay, so let's look on our results. So we implemented 5 protocols. You can see on the left. We implemented it for different number of parties, from 3 up to 110. The execution time here is in milliseconds, and the results are only for 61-bit Mersenne prime. And in blue, you can see the best running time for each number of parties. Okay, so for 3 parties, it's not surprising. The best protocol is the protocol that is designed for 3 parties with replicated secret sharing. For 5 and 7 parties, the best protocol is the protocol that uses the PRSS, the GRR, and the verification based on opening. Then when we move to 9 parties, then it's better to replace the PRSS protocol to generate random sharings with the Van der Monde protocol. From 30 parties, it's already best to replace the GRR protocol for multiplication with the DN protocol. And from 90 parties and on, the protocol with the Van der Monde, DN, and verification based on multiplication is the best. So yeah, so to sum up, you can see that we can compute 1 million gates of 3 parties, can compute 1 million gates, 1 million multiplication gates in about half a second. And 90 parties can compute 1 million multiplication gates in just less than 1 minute, which has never been shown before for multi-party computation. We have some nice figures here. So here we look only on small number of parties, up to 11. And you can see here on this line, you can see this is the protocol that uses the PRSS protocol, and it's average what case? I don't understand. It's a LAN. So you can see the exponential here, the exponential growth, or when we use the PRSS, what we kind of expected. Here you can see the entire results, and the blue line here is the protocol that we said that it has a constant overhead per party per gate, and as you can see, the line is straight. It has indeed linear complexity that grows linearly with the number of parties. Other curves has quadratic growth or exponential growth, depending in different rates. And well, last figure here we have. So until now we only looked at results for the 61-bit Mersenne prime. Here we see a comparison between the best running times for 61 and 31-bit Mersenne primes, and they have almost the same running times, which is kind of what we expected. And I will conclude this talk by saying that secure multi-party computation is indeed practical, even for large number of parties. Thank you very much.
So for your soundness, do you need to take a union bound over the number of gates? or do you get your the soundness 1/f for amortized over every circuit?
What, the cheating? The cheating probability you're asking? No, it's not union bound. For each multiplication gate, this is the cheating probability. It's no. Yuval has a question?
You have a big number of parties insisting on security against exactly half seems like an overkill if you can, say, settle for a slightly suboptimal security threshold and use share packing to, get much better efficiency. So have you considered that?
No, we didn't consider that. Maybe that's a good idea. Thank you.